Yeah. Okay. Okay. So today I'll be talking about the construction of Floer homology for the case of instantons. So I'm not going to outright define what instanton Floer homology is. I'll stick to a very restrictive setting, and we'll see how all the qualitative features play out in this setting. And in the next lecture, we'll get to how do we get rid of these restrictions and go to the most general case. Okay. So as a brief recap of what the finite dimensional situation was, which is what we'd like to mimic. So what we want to do is we want the following setup or the following properties. Want our critical points to be non-degenerate. So if we have a critical point of this, then we want Cn to be non-degenerate. We want our critical points of index k to be sort of like to sort of form our chain complex. So this with a differential that maps from ck minus 1, which is defined by dk of p1, p2, the pairing being the count of a moduli space. P1, 2. We further require, and this is going to be what I'll keep referring to as transversality all the time. What we further require is that M check P minus to P plus is smooth manifold, or actually even C1 will do. So let's just stick with some low regularity. C1 manifold of dimension index of P minus index of P plus minus 1. When P minus is not equal to P plus, and we ask for it to admit a compactification as well. Okay. So one part I want to be explicit about here is that we don't require the compactification to be even C1 in any fashion. We'll be happy with just any topological space compactification, but we just ask that compactification, and let me just, if the dimension of this moduli space is 1, then we want the compactification to be a manifold. But even a topological manifold is good enough for us, right? And just as a brief recap of what M and M check were, so at least formally, what matters to us is that this is the moduli space modeled out by translations, where your moduli space itself is the preimage of 0 of some vector of some section of some vector bundle. So where F is something from sort of path space to some vector bundle, which was in the finite dimensional context, this was defined as gamma goes to the following function, D maps to plus okay, so we want to mimic all of this in the case when f is the Chern-Simons functional. Right? Any questions till now? Like anything that you want me to recall again from the finite dimensional context that would help? Okay, if not, I'll keep going. So let's first start off with talk about non-degeneracy of Hessian. We'll encounter an issue right here, in fact. So recall that the gradient of the Chern-Simons functional at a connection A was minus odd star of FA. So we're working with the three-dimensional story. So this is what the gradient was, which we computed last time. So it follows just from this that Hessian of A of the Chern-Simons functional applied to some connection little a. This is just dt of minus star f a plus dA evaluated at t equals 0. This is just the definition. And what this tells us is that this derivative is minus star dA of A. Okay, so when we ask for the Hessian to be non-degenerate, what we're asking for is that this last expression, minus star dA, that is an isomorphism between the appropriate vector spaces. Yeah. Okay, but there's already an issue over here because if first of all, let's say we're at a critical point and A is dA times psi, then
So if I lost a global view, so are you saying you're going to try to see if the Chern-Simons functional itself is a Morse function?
Yeah, I'm checking whether the Hessian is non-degenerate at critical points or not.
For the sake of trying to make this a Morse function on the space of all SU.
Yes, yes, yes.
So this is still the space of SU2 connections on those three manifolds?
Yes, this is still
not the extensions to the form.
No. Yeah, the four manifold thing was needed only when defining the value of the functional, but otherwise we're solely sticking with the three manifold context. Yeah.
And locally you can always take a tube or something, so you get a formula which is three manifold.
Yeah, I mean, this formula we had derived,
Okay.
we're not even needed to take a tube or anything. We're just taken the four manifold, we're taken whatever path of connections that we had on the three manifold and we extended it to the four manifold. But once we have computed what the gradient is, now the four manifold is unnecessary to keep track of. Yeah. Yeah. So the Hessian is now, in this case, if A were equal to dA times C, this is minus star dA squared C, and this is equal to 0 because A is flat. So dA squared is FA wedge, which is equal to 0 as FA is equal to 0. I mean, that's what is meant by being a critical point of the Chern-Simons functional. So, okay, we wanted our Hessian to be an isomorphism, and it, I mean, even disregarding anything about its range, we have a kernel. So what is going on over here, right? So the first observation to make is that the Chern-Simons functional has some symmetry, right? It's invariant under the gauge group action, and what this is actually, and this is like one instance of the fact that it's invariant under the gauge group. Or let me be more precise about this. So the tangent space at identity of our gauge group is going to be 0 forms on Y, taking values in GE. So GE again at any point x was T belonging to endomorphisms of Dx such that T is Q adjoint and the trace of T is equal to 0. So this is just what it's saying is that pointwise, if you had an SU2 thing, then its tangent space is going to be skew symmetric endomorphisms with trace 0, and you're just saying do that pointwise everywhere. That gives you the tangent space of your gauge group. Okay. So now that we have what the tangent space of the gauge group is, we can look at what the infinitesimal action of the gauge group on the space of connections is. Okay, and we'll get a neat expression for this. So put it in words. Let's say this maps to morphisms of E, and so differentiating what we have is tangent space of identity. Sorry, not automorphisms of E, I meant automorphisms of AE. Yeah. So let me just call its tangent space little odd. What this does is that, I mean, basically the action is going to be like this. T psi acting on A is going to be A minus e power minus T psi dA e power T psi. And you can differentiate this whole thing at T equals 0. So what that gives us is that C has the following infinitesimal action, which is C maps to minus dA of C. So basically just Taylor expand this thing and keep track of which term has the power of T.
What do you mean automorphisms of AE? AE is not a...
AE is your space of connections.
Yeah, but it's not a vector space, right?
It's an affine space. Yeah, so we're looking at affine automorphisms. Yeah. Yeah. But even more simply, what all I mean is that since GE admits an action on AE, so just that means that you have a map from GE into some space of automorphisms of AE. So over here, I'm just using it as a formal gadget. I don't mean to assign it any precise meaning. Yeah, but the point is that I mean, if you want to assign some precise meaning, then affine transformations is one. And the point is that with that understanding, this is the infinitesimal action. So this should always line the kernel of the Hessian. Okay. But that's not it. The Hessian, like just as you know in Riemannian geometry, the Hessian of any real valued function is going to be symmetric. So not only will this be in the kernel, but you also need to restrict the range to be the image of this.
By the way, when you say this is in the kernel, you mean like it's a bilinear form, right? So
yeah, I'm thinking of the bilinear form rather as a map between. So instead of E tensor E to R, I'm thinking of it as E to E dual.
Okay, so that means a Hessian of some things like this,
yeah,
evaluated on some other
thing.
The bilinear form is going to be 0.
Identically 0, yes. And I also mean to say that the image will miss the image of this automorphism because it's self-adjoint. Yeah. Yeah, so this Hessian, when I say this, right, when I write this formula, yes, I should mention it somewhere here. See, A maps from one forms, and it gives you another one form. So this is what's happening.
So, sorry,
Yeah.
again. So this is, you're saying that these are degenerate critical forms. Then?
No, I have not even gotten to the naive definition of non-degeneracy would have been just that this Hessian is is an isomorphism, because in the finite dimensional context, that's what you mean by your matrix having determinant not equal to 0. But now, because there are some symmetries, we have to change what our notion of non-degeneracy even is. The naive notion no longer works. So that's what I'm trying to build up to. What I wanted to say was that, okay, look, here are some automorphisms that, because your Chern-Simons functional is invariant under them, these will manifest themselves as the co-kernel. So there is nothing you can do about it. The only way is to change your definition rather than trying to, change the functional.
And hope that these are the only ones.
Sorry?
You try to pass to a quotient.
Yes, you will try to pass to a quotient at the end of the day, because recall that our critical points, which were irreducible representations, they were finite dimensional only when you passed to the quotient by the gauge group, not outright. So that is the name of the game. You're finally going to pass to the quotient, but to begin with, we're going to stick with this.
Then you have to claim that these are the only ones. If you want to.
Yes, so but that's going to be a hypothesis, in fact. That is not guaranteed either. So, which is why, yeah, I mentioned in the beginning that whenever we come up with we face an issue that cannot be overcome in some naive fashion, we're just going to impose it as a hypothesis. And we're going to keep going just to see qualitatively where that leads us.
Just just to be a bit pedantic, but this Hessian, strictly speaking, it should be a map from one forms taking values in GE to one forms taking values in the dual of GE, right?
Yes,
then
yes.
Because it's SU2, you can identify the dual. The dual is.
Yeah. So that's sort of why this star is showing up as well, because that star, for example, converts your two forms to one forms, and you can be even more pedantic and say the star has to take into account the duality in the Lie algebra level as well. Right. So I'm not doing that, but you're right that I'm identifying the dual of one forms on Y with values in GE with itself by the hot star on forms, and on this thing I'm just using the killing form. Yeah. So in that sense, this is slightly different from what you might expect as the Hessian matrix. But I think in Riemannian geometry, if you just go about this definition, what you get is, you can define. Okay, this is just a side comment rather. So if I looked at the gradient of some function, then I can take its Levi-Civita, its derivative with respect to the Levi-Civita connection, and so that is still now a vector field, right, of sorts. So it takes in a vector, spits out another vector. So in that sense, I've already incorporated the duality right here when defining what the Hessian is. I don't know if that's a very standard thing in Riemannian geometry or not, but this is sort of the definition of Hessians that I've come across.
Yeah, but that's not really a vector field, right? You have to feed.
Yeah, you have to feed in a vector, but you get an output as a vector rather than it being a bilinear form.
Correct.
Yeah, that's what I meant. Like the duality part has already been taken care of in this formulation, even in the finite dimensional context. And yeah, I'm just using that.
So closely related, because you were saying hypothesis. All this depends on the choice of the Riemannian metric, is it? For the various.
Yes. This hot star does not make sense unless I've chosen a Riemannian metric on my 3-manifold.
The Chern-Simons functional itself, does it depend on the Riemannian metric?
No, it does not. It's like just any real valued function. But the gradient of any function depends on the underlying metric, right?
Metric. So will you be able to perturb the metric to ensure non-degeneracy? I guess we'll get to it by.
Yeah, I will get. Maybe there are results of that form, but I think by and large you use other sorts of things.
You perturb the equation itself rather than.
Yeah, because. I can maybe tell you a little more at some later stage, but I think the issue is that the metric might not be good enough for all purposes. It's good enough for most purposes, like for defining, I think, just the Floer homology itself, it's good enough, but sometimes it falls short.
No, but how can you get rid of the non-degeneracy here? Because that just comes from the gauge group, right? That you
I meant the refined version of non-degeneracy that I'll come. Yeah.
It's not non-degenerate.
Yeah. All right. since there was a lot of jumping ahead and stuff, if something's unclear, I can further maybe comment a little bit before moving on. Okay, we'll keep going then. Okay, so all right, to now talk about. So here's, I mean, let me just say out loud what the hypothesis is, and then I'll tell you why it's a good hypothesis, why this is the right thing to ask. So we ask for the image of dA to be equal to the kernel of dA on, these are all subspaces in as subspaces of one form of this. Okay, so first of all, to sort of talk a little bit more about this hypothesis, we know that dA squared is equal to 0. So what this means is that we have a complex of sorts. So we have this complex, and what you should think of this is a deformation of your usual de Rham complex that you see in with differential forms. Okay, so all I've changed is instead of asking for everything to be real valued, now I've asked them to be valued in this little GE, and I still have that it's a complex, and it turns out that you can still, if you go about it, you can still come up with things like Meyer-Wettorys and things like that to tell you that this is all the cohomology groups of this are finite dimensional and such. Okay, that, I mean, one way is developing Meyer-Wettorys and stuff, but we'll appeal to rather a Hodge decomposition sort of statement to get at this hypothesis. So what do I mean by that? What I mean by that is first of all, we have our cohomology groups, which are kernel dA mod image dA, but we can also think of this as kernel of the Laplacian of A. So what is the Laplacian of A? The Laplacian of A is just going to be what you might have seen in Riemannian geometry already. So it's just this, and yeah, the sort of key point of Hodge theory in the de Rham context is just that this is equal to the kernel of your Laplacian. Okay, and even more so, what we can say is that we have K forms Y G. This will be equal to the kernel of Laplacian, direct sum image of dA, direct sum image of dA star. And this is an L2 orthogonal decomposition. Okay. And so now with this, we can in this framework, we can already say two things. The hypothesis is being satisfied is equivalent to asking this cohomology group H1A to be equal to 0. Okay. And another thing that we can characterize is when is a connection irreducible. So a connection is irreducible if and only if H0 of A is equal to 0. So H0 is supposed to be things that are in the kernel of this map dA. So all that is saying is those are the infinitesimal automorphisms of A. So that's like the tangent space of the stabilizer of your connection A. Okay, so irreducibility is asking for your stabilizer to consist of only 2 points. That is, it's being discrete, and this is exactly what it says. So here we are using one special fact about SU2, which is that if you have a stabilizer subgroup of it, then it's discrete if and only if it's the center. So any stabilizer that goes beyond the center has to have dimension greater than 0. Okay. Another thing I ought to point out is that there is a version of Poincare duality for these cohomology groups, and so this is also equivalent to asking for HA2 to be equal to 0, and this is again similarly equivalent to asking for HA3 to be equal to 0. So the good class of connections would be irreducible and which satisfy the hypothesis, which is that all these cohomology groups vanish. So these are going to be, this is what our notion of non-degeneracy is going to be now. Okay. Any questions at this stage? Also, is there anything happening in the Zoom or Teams or whatever?
I don't know, any questions you can?
Any questions for those remote?
No, it's clear.
I don't think that. Two people are signed in, but
Oh, okay.
nobody is asked.
All right. So, okay, under this hypothesis, what is the upshot of this, right? So, assuming we have the hypothesis, what we have is that this is now equal to image dA direct sum image dA star. And so first of all, we can replace image dA star with kernel of dA star, just because the Laplacian has, the kernel mod image dA star is again going to be captured by the kernel of your Laplacian. And since the Laplacian has the kernel, we see that image and kernel of dA star also match up. And what this gives us is that so this tells us that one forms, maybe I should put that, can be realized as you look at the infinitesimal action of your gauge group. That's one component, and then there's an orthogonal component to it, which is the kernel of dA star. So this does two things for us. First of all, what it does is at the infinitesimal level, it tells us what the tangent space of the space of irreducible connections mod gauge is isomorphic to the kernel of dA star sitting inside. This, so okay, this is great because now we have what the tangent space is, and we can say that under our hypothesis.
Wait, what was BE?
Oh yeah, BE is the space of connections modulo gauge. So BE star is AE star mod gauge.
And so AE star are the irreducible.
Yes, yeah. Let me also.
Irreducible but not necessarily flat, is it?
Yeah, not necessarily flat.
So, sorry, since I'm slightly lost track. So A is now a flat connection in all this hypothesis. Right?
Yeah. For the hypothesis, A is flat.
A is flat. So
Yeah.
then what you have is a bundle with flat connection, and these cohomologies are just the cohomologies of the twisted coefficients.
Yeah, the twisted Dirac complex.
Oh, you take the twisted Dirac, which could also be done in algebraic topology, but whatever it is, yeah.
Yeah.
Can you just go up for one moment?
Yeah.
So just globally see all these things.
Yeah, I can maybe try zooming out a little bit as
Zoom
well.
out and go down a little. Yeah. So a little bit below for the definition. No, the other way.
Oh, sorry. Yeah.
Earlier. So you have a flat connection, and the boundary is the boundary on. So your D, which is the usual exterior D, gives you bound together with a connection gives you differentials on the bundles.
Yeah.
And this one has zero homology is your hypothesis.
Yep. So first of all, when A is flat, you get a complex, and
Yes.
we now ask for the complex to be acyclic.
Yeah. So when it's flat, you get a complex which just corresponds to the representation, the flat bundle corresponding to the representation. But yeah, that is not relevant to what you're saying, but
Yeah.
it's true. And so what you're saying is that this twisted denom cohomology, which will also be the twisted cohomology, presumably cohomology with coefficients in the module, which is the representation, is zero.
Yep.
Is zero,
Yep.
which is
Yep.
hypothesis under which you're going to be defining Floer homology. So this is ordinary, not Floer homology, but just.
This right now has nothing to do with Floer homology at all.
So what your hypothesis is that I got confused for a moment that your.
Yeah, the hypothesis admits
hypothesis is that twisted cohomology itself is zero.
Yeah.
And
So
that will let you give some decomposition of spaces of forms.
yeah. So
Okay.
the point is that once we're in a flat connection, we have a twisted Deram complex.
Yeah.
And this affords us to now, decompose our space of forms where each piece has like some significance, and one of the pieces has a cohomological interpretation.
Okay.
And we ask for exactly that subspace to vanish.
Yeah.
So is there a condition, a hypothesis on the topology, the manifold that will imply this?
No, you cannot ensure this at all. Even for ciphered fiber spaces with say more than 4 singular fibers,
But
you will not be able
homology
to.
spheres will have this, right?
No, even take ciphered homology spheres with more than 4 or greater number of singular fibers, you will not be able to satisfy this.
Because homology with twisted coefficients can be non-zero, even
Yes.
ordinary homology
Yes.
is zero.
Exactly.
That's the group cohomology is the rank.
Yeah, but instead of trying to think about the group cohomology or such, because
No, I'm
the
saying this
bundles.
cohomological dimension is defined in terms of how many minutes. So only
Yeah.
for free groups do you have higher homology.
Oh yeah.
Sure.
You're right.
Twisted
So
coefficients, it's non-zero as long as it's not a trivial group.
yeah.
And H2 can also be non-zero.
So yeah, we cannot a priori ensure anything of that sort. And in fact, the local coefficients, so to speak, will depend on the connections themselves. So you can't even give it just, essentially the point is that GE with its connection need not be trivial. So you can't even give it a Lie algebra cohomology interpretation as well, a priori. It's that, but twisted again with like some local coefficient system. And in fact, you can even have like 3 manifolds that are not homology spheres, so that have even B1 greater than 0, but all of these could vanish for specific connections. So while they're somewhat related, it's nowhere as naive as would think.
Well, also, all 3 manifolds, the group will be cohomological dimension 3. So there will be some twisted coefficients for which it will not vanish. It's just that if you're unlucky, they will be the ones that come from instantons, but you can't rule it out.
Yeah, I mean, even if you just take the trivial connection, right? Then this the GE thing can be tensored out, and since you're working with universal coefficient will just tell you that it's whatever cohomology group of your manifold just tensored by the Lie algebra, and so H0 will always exist. If your thing is flat, I mean, if your thing is the trivial connection, then H0 that's going to be one-dimensional regardless of what 3 manifold you choose. So yeah.
So your hypothesis below H0 vanishing doesn't hold for the trivial connection.
Yeah, it does not. So I asked for irreducibility specifically.
Okay.
Yep.
Okay.
Yeah. Yeah. I hope that does answer your question.
Yeah.
Okay. 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 So before we went off on that digression, what I was about to say was that at the infinitesimal level, we know now what the tangent space, how the space of connections modulo gauge looks like, the space of irreducible connections modulo gauge. So I will play fast and loose with writing this irreducibility thing on your space of connections mod gauge, because the other subspace, so the space of reducible connections, has infinite codimension. And when you take it mod the gauge group, then sometimes some of them might become finite dimensional or such, but the algebraic topology of BE star and BE basically coincide. So for the most part, sometimes I might write BE when I really mean BE star, in which case do ask if that's too confusing. But yeah. Okay. Okay, so now we know what the infinitesimal configuration space of connections look like. I'll refer to this as the configuration space of connections. And we want a chart out of this now. And we can actually get a chart just by using standard theorems of differential topology. And the chart that we get is as follows. We ask for A be this, with A minus A naught. So let's call this connection A naught for a moment. This to be small enough. And we ask the A naught star A minus A naught to be equal to 0. So this is a chart near the connection A naught. And so this is typically referred to as the Coulomb gauge fixing condition. So typically when you mean gauge fix, all you mean is some subspace of one forms that's complementary to the image of the tangent space of the gauge group. What we are doing is we are being very specific and asking it to be the L2 orthogonal complement. Okay. So there's a chart, and by our hypothesis that the Laplacian has no kernel, what that tells us is that dA restricted to this subspace is going to be injective. So that's great. So what that tells us is, under our hypothesis, at least the Hessian is injective. But what about surjectivity, right? So I need to tell you about that. And yeah. So as I mentioned, the Hessian is going to be self-adjoint. So what we should really be looking for is the surjectivity of this operator. So map from kernel dA star to the kernel dA star. Okay, where it's given by the same expression. So z psi maps to minus star dA psi. And you can again appeal to the Hodge decomposition to tell that under the hypothesis, this map will be surjective as well. Okay. And I mean, this one fact beyond just the Hodge decomposition I've talked about so far is that dA star is, okay, I always get confused about the sign over here, but basically it's take Hodge star, hit it with the twisted Dirac differential, and then again take Hodge star, and then there's a sign that needs to be checked to make it the L2 adjoint of your exterior derivative. Okay. So what you should think of is that this, while it's in the kernel of dA star, this is actually mapping to the image of dA star. And you can use just a little bit more of symbol chasing will tell you that when the hypothesis is satisfied, this is surjective as well. But there's a problem in the sense that we now need to keep changing our space on which we check whether the Hessian is non-degenerate or not, depending on the connection itself. We'd like a slightly better reformulation so that we don't need to keep changing our vector space, because this is not even a finite dimensional vector space, so it's going to be pretty messy to keep track of how it changes. So we define an operator dA as follows, which maps zero forms, direct sum, one forms to, again, zero forms, direct sum, one forms. So we can write this as a square matrix. And here's the block matrix form of this. Stat minus dA minus dA star and star dA. So what this does to zero forms is it on the zero form level itself it's zero, and it gives you a one form that's minus dA. This you should think of as the action of the tangent space. Sorry, this is not. Sorry, what this is doing is this is trying to fill out the complementary subspace to kernel dA star in the image. Okay. And on one forms, this is the Coulomb gauge condition. So you're already modding out by the gauge group to begin with. And then this is the Hessian that we talked about just now. Okay. So first of all, dA is self-adjoint. And kernel dA is equal to H0 of A direct sum H1 of A. So now our non-degeneracy condition is going to be dA is an isomorphism, and that takes into account both the irreducibility and our hypothesis all in one go. Okay. Yeah. Oh, yeah. I want to mention in general to the people who knows these terms, dA is a Fredholm operator, and so you can, and since it's self-adjoint, it's index zero, and what we are asking it to be is it to be a generic self-adjoint Fredholm operator. That is just to say that you have, even when the hypothesis is not satisfied, you have some hope of being able to perturb it to make the right thing happen, because it's a generic condition. Okay. All right. So from here on out, we put two assumptions for the rest of today. The first assumption is that Y is an integer homology sphere. By that, what I mean is the singular homology of Y with Z coefficients is isomorphic to singular homology of 3 sphere with Z coefficients. Okay, and all connections are irreducible unless stated otherwise. Okay. All right, any questions up to this stage? I'll next be moving on to talk about the moduli space of trajectories. Okay, fine.
I have
Let's
one clarifying question.
now talk about.
So just to be clear, given a three manifold, this is a non-trivial condition, right? That there exists a vector bundle E and a connection which satisfies these hypotheses, right?
Yeah, it's not always satisfied. Yes. Yep. Okay, so just before we start talking about the moduli space of trajectories, I want to mention that wherever we have formulated what our moduli space of trajectories, what its dimension is and such, we talked about the index of our critical point, right? So the index what we said was it was, whatever, how many ever negative spectral directions are there. So like how many ever eigenvectors with negative eigenvalues are there as part of your Hessian. Okay, so the first observation is that the spectrum of the Hessian will be reflected in the spectrum of dA. That is to say that any eigenvalue that's there will sort of show up here as well. Okay. With that, the point is that since dA is a self-adjoint, this is a differential operator. So you have a self-adjoint differential operator on a odd dimensional manifold. It's just a general statement that in such a context you have spectrum unbounded in both directions. So there are infinitely many positive eigenvalues and there are infinitely many negative eigenvalues. So there is no way of talking about the index at all, because you want to take the difference of indices, you're going to just have infinity minus infinity, which never makes sense.
So, can you repeat your statement?
Oh yeah. So yeah. So this is self-adjoint differential of odd order plus on odd manifold, odd dimensional manifold, implies spectrum of dA unbounded in plus or minus infinity.
Unbounded above and below.
Yes. Yes.
So odd order is the key.
I think that base manifold also needs to be odd dimensional, but maybe.
How does that base manifold even play a role? Because it's acting on sections on.
I mean, just take G to be the trivial bundle, right, and A to be the trivial connection. Then, then this sort of like your usual D plus D star, your Hodge operator on your three manifold or whatever, right? Over there, if it were an even manifold, then in fact this has non-trivial Euler characteristics. So, for example, that will get the symmetry mixed up wrong. I think this is also required, but I don't know of a reference that says this outright. But that said, I will encourage you to think about the trivial connection on the 3 torus. And on that, you can explicitly compute what the spectrum is, and you'll see that it's unbounded in both directions. So yeah, that should be like the first toy example check. And I think this is, I think you can reformulate this. I mean, this is a random comment that I just want to make, and it will not be of much.
In Torus case, will it just be plus minus n or something like that? Or
yeah, I think so, because everything will split up into the
or
circles.
root n or something. I mean,
yeah, depending on how you
the squared
normalize.
of this is the Laplacian, so the eigenvalues
Will be, yeah.
I see.
One extra comment that I want to make is that you should really think of dA as like some sort of Dirac operator of sorts, because if A were the trivial connection, then this really captures the the spectrum of the square root of the Laplacian, and like one way to interpret that is
Maybe
thinking of
odd is relevant because bicollinearity exchanges even in odd, and so spectrum might in odd case might actually be symmetric under negation.
Yeah, that was sort of what I
Every
wanted
time you
to.
have a positive eigenvalue, you have a negative eigenvalue with the opposite form. I mean, Poincaré dual to that.
Yeah, but I don't want.
Unbounded is unbounded on both sides. Actually, but that may not be true with twisting and so on. But at least
Yeah, but I think if you have self-adjoint, it does not follow as neatly as that. But
and in special cases, at least it must be unbounded on both sides because of symmetry and the negation.
yeah, sort of. I mean, just you have some symmetry in the case of the circle, you have some sort of symmetry, and that you can exploit that to get this unbounded thing. But yeah, I mean, the point that I wanted to make was that this is not something you can get rid of under generic perturbations or anything like that. This is a fact you need to live with.
the spectrum of the Laplacian or second order operators will be unbounded in general.
Yeah.
Second order elliptic operator. So if you think of this as some kind of square root.
I mean, you could always say it was a positive square root, right?
Oh, on
It
both
will
sides.
not be.
Yeah,
it
yeah,
will
it's the
not be
claim.
unbounded. I mean, it will usually be positive.
Yeah, for second order things, typically they have some sort of positivity condition of sorts.
It will be on one side.
Yeah. So here the claim is it's on both sides and you can't do anything better. Okay. Nonetheless, we're going to try constructing our moduli space of trajectories and it'll become clear what the right reformulation of the index would be. So it'll turn out that we can never define an index of just a single connection, but we can talk about the difference of indices of two connections that we give. Okay. So, all right. So towards that goal, let AT be path of connections. So what I mean by that is gamma t equals AT or A sub t is your path of connections. Then the gradient trajectory, which was
So Deeparaj, to clarify, you're going to talk about difference of indices of two flat connections, right?
it'll turn out that even flatness is not necessary.
Not necessary.
Yeah.
Just arbitrarily.
Yep, yep. But for our context, we care mostly
We'll
about
apply
the
for flat, but it's true
Yeah.
even without flat.
Yes,
Defined
yes.
even without flat.
I mean, and the reason for that is the operator that I just mentioned, that makes sense even if it's not flat.
Mhm.
And you can still ask for it to be injective or surjective or whatever. And more important, yeah, much more importantly, it's going to be Fredholm regardless of your connection. Okay, so we have this equation, which just is that A dot T is equal to the three-dimensional Hodge star of the curvature. Okay, so let's reformulate this in terms of something on R cross Y. So let's call B equals.
Oh, sorry, there's a question here in the chat.
Oh, yeah.
Yeah, so
Actually, maybe
one,
I can
one
see it
question.
right.
No, I mean, it was a raised hand.
Oh, okay.
Yeah. So can you hear me?
Yes.
Yeah, okay. So the question I had was this operator capital DA, this is just sort of combining the complex which is given by omega naught to omega 1, which is DA star, and omega 1 to omega 1, which is DA star plus DA, right? That is, it's this elliptic complex but turned into an actual operator. That's the first question.
So that you'll have to repeat it to me because I can't quite hear it from here.
Okay.
Just one more. So the operator, I'll just repeat it out here. You could not hear there.
Yeah, I could not.
Yeah. Can you repeat? I'll speak it out.
Yes, I can repeat. The operator capital DA is the elliptic complex given by omega naught to omega 1 dA star and omega 1 to omega 1 dA star, dA plus dA star, the Dirac.
Yes.
That elliptic complex combined into one operator, right?
That operator is two elliptic complexes, omega naught to omega 1 and omega 1 to omega 1 star combined into one, right?
Yeah.
Okay, that's the one question I had. And second question that I had was the fact that this index is not defined by the relative index is defined. This is a consequence of the fact that the Dirac operator has index 0.
Repeat it out.
Is the fact that index is not defined but relative index is defined a consequence of the fact that Dirac operator has index 0?
Yeah, can you repeat it? I'll speak it out.
No, I would call it as a consequence of the formalism of Atiyah-Patodi Singer-Index theorem, and
Yeah,
which I'll get to in some time. But the moral story is that you have an elliptic operator. Once you have boundary conditions, you can still define an index. But if you just have an elliptic operator on a non-compact manifold with no boundary conditions or no real control near infinity, then you're lost.
So for example, in the fact that the relative index is defined would be because your gradient flow lines give rise to 4 manifolds, so 3 manifold cross I's, for example, and there you have the Dirac operator d plus d star
So
whose
the
index
fact
is defined,
that
right?
the index is defined is because your gradient flow lines give rise to 4 manifolds, is it?
Not outright either. It's going to be part of a much more general framework. I mean, I'll only touch upon that framework, but there's a whole bigger story there.
Okay, thanks.
Yeah, so just to add, the indices are sometimes defined only mod 2 or mod 8 and so on, so it's complicated reasons.
Yeah, I'll actually get to explain about the mod 8 part. So, yeah.
In this case, it's mod 8, is it?
Yeah, in this particular case, it'll turn out to be mod 8, but in more specific constructions where we want to get rid of things like the hypothesis, it'll become mod 4, I think. And in Cyberguten land, it's typically mod 2, Cyberguten or Fleur. Okay, so first let's reformulate what the gradient.
Floer homology is actually mod Z, I think.
There again, it depends on what the ambient manifold is. If it's S3, you're in good shape, but if not, you're again in trouble. Yeah. So, okay, here's a connection that we have on R cross Y, and let's see if we can write down what the equation is in terms of the connection B. Okay, so first of all, FB is going to be minus A dot T wedge TT plus FAT. Okay, so what this means is that so with that expression in mind, this is equivalent to the 4-dimensional Hodge dual. So what I mean by the 4-dimensional Hodge dual is you're taking Hodge star on R cross Y instead of just on Y. This is equal to minus F of minus the curvature of P. So typically this is abbreviated to FP plus is equal to 0. So I should make a couple of comments over here. First thing is that on a 4-manifold, the Hodge star operator, you have Hodge star operator mapping from 2 forms to itself, and it turns out that the square of this operator is plus 1. So what that means is we can spectrally decompose it into eigenvalues plus 1 and minus 1, and the plus part is supposed to denote the projection to the plus 1 eigenspace, and there's a minus part which denotes minus projection to the minus eigenvalues subspace. And so now what we're asking is that our connection is negative subdual, so that is that it satisfies this, that it's an eigenvector with eigenvalue minus 1, and so that's asking for the projection to the plus part to be 0. Okay. What this reformulation has the advantage that now earlier we only had gauge symmetry on the 3-manifold. So what we could do was the symmetries of this equation would be like R to gauge transformations of Y. But now reformulating it this way, we have gained some more symmetry. So what we have got is we got all gauge symmetries on R cross Y itself. Okay. So this is crucial in the sense that earlier whatever sort of linearized operator you would have tried defining would not have had the right properties, but now with this additional symmetry we'll be able to kill off we'll be able to kill off some more things, and that will allow it to become from, I think, an underdetermined PDE to to neither underdetermined nor overdetermined. There's a word for that, right? I'm forgetting it. Okay.
Determined, I suppose.
Yeah, I'm not sure. Anyway, so with this in mind, we're going to redefine the path space a little differently. So it's this B looks far more. B so there's a connection on R cross Y with the following properties. So locally B looks like, I mean not locally, this is the global expression, plus AT plus Ct dt. So Ct is some function defined on R, where so At converges to the right thing as t goes to plus or minus infinity, and Ct goes to 0 as t goes to plus or minus infinity. So the reason we put this Ct thing is so that you have an action of the gauge group of R cross Y on this path space. If you had demanded Ct to be 0 all the time, then you would have been stuck in the earlier situation. Okay, so we have this. Now, so we fixed some connection A0, which is in the path space. So what I mean by that is,
So when you say B on R plus Y, B is what kind of creature on R?
oh, sorry, yeah, connection.
Just a connection.
Yeah,
That's fine.
yeah. So let's fix a reference connection of the following form. So that's what I should say.
So it's of the form del T plus what is the difference? A of T plus what kind of creatures are those?
C is just a function. A is a connection for each time. A is a connection on Y.
And is the decomposition supposed to be unique, or you just write it in this form?
It's unique. Yeah, there's a dt factor over here sticking out, and this. So in the dt direction, you have this differentiation along the t thing and ct dt. So that's supposed to be a deformation of the usual time derivative. And then on the three manifold directions,
time direction, fine. So
Yeah.
this is the okay. So the
yeah,
first two terms are the horizontal part of the connection, and the third term is the vertical part, or whichever.
the first and last are the horizontal. I mean, the
Oh,
time
okay,
directions,
okay.
and the middle part is the
Fine.
y
Yeah,
direction.
yeah,
Yeah, I would rather not call them horizontal and vertical
No,
directions,
I mean, use the
yeah,
but I mean one side of the whole
Yeah.
product and the other side
Yeah.
of the product.
yep.
Time and space direction.
Yep. So let's fix a reference connection of this sort. So this we actually take under gauge. This is your path space, and just find a representative del t plus at. That is a representative where ct is equal to 0 all the time. And it turns out that for any connection in your path space up to gauge transformations, there is always such a representative. But we fix such a connection. Let's call this A0. Then our sort of the trajectory equation is now going to be FB plus. That was the thing that we just now saw. Plus,
So, just to
Yeah.
get the notation right, so you're thinking of, I mean, that's something like B naught. I mean, you want to call that B naught because that belongs to the path space, and then you're basically looking at
yeah,
that
sure.
evaluated at 0 or something like that.
Yeah, but I want it to be of the specific form where it's temporal sort of thing. That's why I just called it A0. But yeah, B0 is also a fine enough notation. But yeah, the crucial part is that we've chosen a representative B0 which has no CT component. Yeah. So this is going to be so.
Question, when you're saying gauge transformation on R cross Y, you have a separate one at each time. You're allowed, or common one on all of one?
It need not have any slice-wise decomposition.
Oh, gauge transformation of what gauge group is this?
So you
Oh,
just
it
pull
need
back
not
your
even be a
thing.
product, yes.
Yeah, you pull back your thing on R cross Y, and
It
then you
need
do
not
things.
even be a product.
Yeah,
Okay.
yeah.
No, but so you wanted to preserve the boundary condition at infinity, right? So C of t should go to
0.
0. So does that impose some condition on the gauge group at
Yes.
The
These
boundaries
the gauge groups need to go to identity
Identity
near
at the boundary.
plus or minus infinity. Yeah. Yep. To not to anything in the center. Anything in the center is fine. I think. Yeah. 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 I'm sweeping some of these things under the rug because I won't be going into too much detail about the analysis in this context. I'll mostly just be sketching ideas or like saying some comments. So which is why I'm not being very precise about some of these details. But yeah, if they're confusing or bothersome, then feel free to interrupt and ask. Siddhartha, did you have something you had planned? Okay. Okay, so our yeah, so our space, the thing that we want to cut out our moduli space by, that equation is first going to be the gradient trajectory equation itself, and then we're going to put the gauge fixing condition. So that's going to be b naught star b minus b naught, and this thing will turn out to be elliptic, but that's not good enough to say so sorry, yeah, what I mean is the linearization of this equation is going to be an elliptic differential operator, but that's not good enough to ensure Fredholmness of our operator f. But it'll turn out that with the right boundary conditions, which is basically just this, it will turn out to be Fredholm. So let me say a little bit about that. Let me rewrite what the linearization of this is going to be, and it's going to just become somewhat apparent what is going on. So let's take, how do I write this? Okay. So let's take gradient of this by, I mean, sorry, not gradient, this is just the derivative of. So we can write this in these coordinates where little b is supposed to be things in the 3-manifold direction and c is supposed to be things in the time direction of a tangent space. So now this is going to be, you first take dot, and then you take this thing. So you should not think of db naught as being fixed. It's more like for each time slice, it's d of at that time slice. And so what you should think, what the upshot of this of rewriting it this way is that so this is elliptic because of the way it's been formulated. Like, it's one part is the IISc equation, the other part is the gauge fixing condition. So you can check that it's elliptic by hand. And by writing it in this format, you can explicitly see what the boundary conditions lead you to. Like, what you will have is that if you try writing some bound of let me just call the vector v. If you try writing some bound of this sort, then asking for v to be in, say, L2, for example, L2 1. So you want it decaying at both ends, and you want it to have first derivatives also decaying on both ends. Then this turns out to be whenever db naught is invertible at the very end. So in the middle, you don't care about what happens to it, just that it's Fredholm. But at the very end, you need it to be an isomorphism. In that context, what you get is, okay, let me not use these analysis specific notation. Let me be just more. Anyway, this is a comment aimed particularly at the analysts rather than anybody else. L2. Yeah. So you get bounds of this sort.
What is capital D B naught?
Oh, it's that operator that I wrote out.
Oh, that matrix.
Yeah, when discussing the Hessian.
That seems wrong. I mean, you're already differentiating on. Shouldn't it be the other way around? That L2 because you're already differentiating on the left, right?
Yeah.
The L2 norm of that is controlled by.
Yes, you're right. So, okay, no, yeah. Well, the statement that I want to say is the following: if a of t were constant and d a of t were invertible, then indeed the L2 norm of this is controlled by the L2 norm of V itself. Yeah, this is what I want to say. And yeah, this tells you that the image is closed and that it's injective. and you can check that the adjoint of this is going to be adjoint is NHTT plus naught, and this thing again is injective. So that means that this, when AT is constant and this is an isomorphism, then this operator is an isomorphism. And since you know it's already Fredholm, you can do some cut and paste arguments to sort of tell you that in this case where B0 is only asymptotic to connections A plus or minus with D A plus or minus isomorphisms, then you can tell that this is actually Fredholm. And the part of the broader story that this is a part of is, well, on one side it's part of the Thea-Patodi-Singer index theory. On a more sophisticated level, this is part of, I think, Melrose's B calculus. And I think there's...
So normally you need some weighted spaces, right? So in this case, you don't need...
This is an isomorphism is what allows you to get rid of the weights.
I see.
Yeah. Yeah, typically you're right. You need weights, because if the asymptotic operators are not isomorphisms, then you have issues. But yeah, typically even in the cases where you need weights, right, your asymptotic limits are still going to be self-adjoint typically.
There could be self-adjoint, but
but you could have some kernel. Yeah. So you use the what all the weight does for you is achieve this condition. Right. Is my point. Right. So yeah. So if you have this condition, then you don't need anything more. Yeah. Okay. I'm not doing great on time, so we'll see how this goes. Anyway, sorry the discussion went off completely towards the analysis, but are there any other questions, analytic or topological so far? Okay. Right, there's nothing. Let's keep going. So since this is going to be Fredholm, the linearization is Fredholm, we can talk about what its index is. And we'll call this the virtual dimension of the moduli space. Plus equals index. So I've added a subscript Z over there, which by that what I mean is that so our path space, right, it has different components. So it has different pi 0. And the Z just keeps track of which component of the path space you're in. And so given a path space component and asymptotic limits A minus and A plus, we can talk about the relative grading, so the relative index of sorts, which is just computed as the index of this linearized operator. And in favorable cases, which is when transversality holds, our operator is going to be surjective everywhere. And so instead of index, you can call this the dimension of the kernel. So yeah. Okay. Let's see.
So the choice made here is choice of components when you're taking relative index.
Yes. So yeah, just beyond the asymptotic.
If there was just one component, this would give you an absolute index as well.
No, there will never be one component.
Huh. I mean,
Yeah. I mean, I don't want to mess too many things together, but yeah, in this context, there will never be one component, and I basically
the point is that
don't know.
A choice made so far, which is the choice of component, and you have to figure out what is that choice.
Yeah. I mean, basically, the point is that this moduli space will split into distinct components, and the dimension is only locally constant. So on each component, the dimension will take different values.
Right.
Yeah.
But it doesn't take just absolutely any value, or you would have no index at all, but they're all equal mod 8 or something.
No, this is not. This is an integer. This is not mod 8 or anything.
No, but the dependence on Z given A minus and A plus is mod 8 or something, or not?
Yeah, we'll come to that. But right now, when talking about the moduli space, this is an actual integer.
Yeah, no, that
yeah.
Sure. This is an actual integer depending on the component.
Yep. Okay. With the time that I have left, let me just what else do I want to cover? Okay, I'll get to those in the next lecture. Yes. So, right. Okay. So let me just give a flurry of facts about this relative grading. I'm going to switch to calling these grading rather than indices because for whatever reason, all the literature just calls them grading. Defined not critical points. So to define this, we don't need a plus or minus to be critical points. They can be anything as long as they are not degenerate in the sense that the DA operator that I talked about is invertible. And you have a gluing formula of sort. I mean, not a gluing, but sort of additivity formula of sorts. Z plus. Okay. So if you had like path component z minus of paths from a minus to a naught and similarly z plus from a naught to a plus, then the sum of their relative gradings sum up to the grading of z from a minus to a plus, where z is just concatenation of z minus and z plus. So exactly what you'd think would happen for if these were difference of some indices is what happens. Okay. So this is what Siddhartha was mentioning a little while ago. I'll be talking more about this in the next talk, but for now, let me just state it as a fact. So when both the endpoints are the same, z is a closed path, and so all that I'm really saying is that gr z of any two things is going to be 8 times an integer whenever z is a closed path. Okay. And so there is a unique connection, which is the trivial connection sitting inside the configuration space of connections. And what this does for us is that we can define sort of grading of a connection A with Z mod 8 with when A is irreducible. Oh yeah, I should mention this over here also, when A is irreducible.
If A is a critical point, then there can't be a closed path, right?
There can be. You could.
So you are looking at trajectories.
Yes. So the Chern-Simons functional is R mod Z valued, it's not real valued. So that's why there could be loops. Yeah, that's why I've been insistent about this loop business. But it'll turn out that if you have seen Morse Novikov theory, so over there it's has to be defined with a Novikov ring, and the only time you can define it without Novikov rings is when the function, it defines a class in the first homology group of your base manifold. And whenever that's 0, only then you can define things with integers. But in our context, magically, we don't need that requirement. We'll still be able to get it over integers. And that is something very specific to infinite dimensions, which has no analog in finite dimensions. And I can even tell, I mean, I can tell more about why it has no analog in the next time. I thought that I might have enough time to get to it today, but I don't.
What do you mean by that unique? You mean there is some canonical zero?
Sorry?
There is a unique theta belongs to B.
Oh, this is the trivial connection.
Okay. So uniqueness means you have a canonical.
Yeah. I mean, there's a unique gauge representative, and over here I'm using the fact that Y is an integer homology sphere.
Okay.
Yeah. Or am I? No, I'm not. I think. Yeah, I'm not. I don't need anything. It's just the trivial connection is corresponding to the trivial representation on the fundamental group, and it's defined no matter what. Yeah.
What was BE?
B is the configuration space of connection. So that's connections mod gauge.
So irreducible connection. Okay.
Yeah, or irreducible. In fact, over here, let's stick with irreducible. Okay. With this, okay, here's what we've covered so far. So far, I've told you, okay, this. Now this is no longer a chain complex over with integer grading. It's going to be with grading Z mod 8. Nonetheless, we can still define this in groups, which is K mod 8, A flat, and irreducible, and the differential is over all paths and connections B, which are inside the next complex, with GRZ AB is equal to 1, and you just okay. Now the first question ought to be over here is that you're taking now a union over Z as well, right? So why is this now finite at all? And that and this story about Novikov rings and whatnot, and that's one thing to be discussed. Another thing to be discussed is about compactness, because I'm told you until now nothing has been said about why d squared has to be 0. So I need to explain that as well. And both of those and about some explicit examples I'll do in the next talk. Yeah. So I'll end my talk today here. Are there any questions in the chat?
So this is Instanton Floer.
Yes, this is the chain complex. This is the differential, and this is Instanton Floer homology.
This is Floer's paper.
Yeah, this is originally due to Andreas Floer in his paper about Instanton Floer. I think it's called a Floer homology on connections or something. Not sure what the title of the paper is, but yeah, this is the first paper on his first paper on Instanton Floer homology does it in this way. Maybe not in this, modern and sophisticated language, but essentially this.
I guess the title wouldn't have Floer.
Yeah, that's what I was wondering.
Because it's written by Floer.
Yeah.
Not with the Instanton.
Yeah.
Yeah. I mean, people typically just say Instanton homology to refer to Instanton Floer homology. So,
But what was his motivation in defining this?
his motivation was, let's see, I think by that time, historically, like Donaldson had already talked about the ASD equations and such, and he had already, sorry?
Instanton invariants were before this, Donaldson.
Yeah, so the Donaldson invariants were already there, and the expectation was that this is part of like some TQFT framework. So for 4 manifolds, you have numbers, and the hope was to get some vector space thing for 3 manifolds, and Floer sort of realized that vision.
Mildly slight historical reversal, but basically gluing theorems. Suppose you take a 4 manifold that's
Oh yeah, but there were gluing theorems even before this,
right,
I think.
But I think the gluing theorems were there only when things were in some sense vanishing clear homology.
Yeah. So you had connect some theorems and stuff, but like.
As I understand, the point is that if you take a 4-manifold with a 3-manifold contained inside it,
Yeah.
you can prove things. I mean, you can prove all the Tom conjecture, this, that, by you take the 4-manifold, make it into a dumbbell, make a long neck, which is that make the 3-manifold into an enormous cylinder and just two stumps, which is the more 4-manifold on the two ends. And then Instanton solutions will look almost like pipes going through this. And hence you will get a relation with Floer. This is what Deeparaj was saying about TQFT. So if you have a 3-manifold, and then you could just make the Riemannian metric so that the 3-manifold cross interval becomes enormous and the rest of the 4-manifolds are really interesting. And it becomes smaller. And then any solution to an appropriate PDE will be more or less a solution on one piece, the other piece, and something that goes through the pipe. And the first gluing theorems were where the things going through the pipe were boring.
Yeah, so
Floer homology, you will get the equivalent of Meyer-Wertheis, where you actually have interesting homology going through the pipe, but you still now have a combination of the glued manifold in terms of the two pieces.
Yeah, but I should mention that. So in this framework where you have like say, an integer homology 3-sphere that's embedded, and you stretch along this, right?
Yeah.
You will. I mean, this does not do everything because this chain complex has no talk about the trivial connection at all. But what you could have is two pieces where it's irreducible on one piece, trivial on the other, and so trivial on the tube as well. And now there is going to be that contribution that's not captured by this TQFT framework. So it's in the Instanton case, it's much more sophisticated.
This is not a complete answer, but it gives some answer even in the case where you know Floer.
I think this never. I mean, just this naive thing never gives you an answer. You need to go to this sort of refinement by Froschow that takes into account what the trivial connection is doing as well. And so it's but I would say that naively if you wanted a TQFT, this is the first thing that you would attempt.
So TQFT for 3 folds you want
vector space,
and then once there's a cobordism there should be some
sort of gluing. And so
also 4 manifolds without boundary should give you
numbers. And 4 manifold with one boundary component gives you an element of that vector space. Right. And there's a pairing on this vector space. So if you had 2 4 manifolds bounding the same 3 manifold, then you could take those vectors and take the inner product under this vector space, and then that gives you a number. So that's the sort of gluing result.
Because the opposite orientation.
Yes, then you have a duality. So yeah. And now you just use the duality pairing. Yeah. Yeah, I have decided.
It seems, I mean, because how do you apply these things? Because the hypotheses itself are quite non-trivial conditions, right? And
So
you verify that you do have such connections that.
So that's first is to really try hard and understand what the moduli spaces were, and this was done to some extent by Fentuschel and Stern and some others. But then the sort of cheaper alternative was that connect some of these such that everything has the right things. And so now, the original manifold might not, but now you connect a piece to it. And this piece will ensure that everything happens.
That stops work, is it?
No, not quite. I don't think this is Stobbs's work. I mean, it's going to be very simple. Like you add a piece with some non-trivial SO3 bundle. And now this piece will ensure that all your connections are irreducible. And the part about ensuring non-degeneracy, you can just perturb your thing. But yeah, I think the way of perturbing through Riemannian metrics was due to Cliff Tobbs in the 4-dimensional case. And then I think his techniques go over in the 3-dimensional case as well. Tobbs and I should probably even mention Uhlenbeck at this stage, and maybe some other people. Dan Fried also might have been involved in this. I can't recall explicitly who are the first people to go along that framework. But it turned out to be, for a lot of things, it turned out to be cumbersome to keep changing the metric because then you could lose some symmetries and things like that. So that the symmetry part has not yet been resolved, but like these other perturbations that you can make, they are in some sense nicer and like allow you to get genericity of all moduli spaces, not just the low-dimensional ones. The metric perturbation business of Uhlenbeck, Tobbs, and others works only for low-dimensional moduli spaces.
By other perturbations, you mean taking connected sums with other?
No. The connected sum part is to ensure irreducibility. To ensure non-degeneracy, there is another class of perturbations which were originally due to Andreas Floer called cylinder functions. And those, yeah. There are quite a few layers to this. I mean, which is why I chose not to talk about gluing in this whole 2 weeks. I'd rather talk about the low-dimensional topology implications of these things. And one part which you rightly mentioned is, okay, even if you satisfy all of this hypothesis, right? How do you compute anything, right? So over there, sometimes again you can explicitly, like for ciphered homology spheres, you can explicitly compute everything that you need, and it'll turn out that the moduli spaces are actually rational varieties, so they're birational to
But
just
ideally,
complex.
I mean, you would want to compute things without having to glue things on, right? Because I mean, abstractly, that's a good enough thing. But I mean, to actually compute things, you can't glue. I mean, you can't connect some things and then try to compute.
No. It turns out that when you do these connections and these pieces are nice enough, you can actually tell what the representation, how the connections and everything change in a very explicit fashion. So, I mean, you might have seen this in some other frameworks, like sort of like Morse gluing theory and things like that. But the point being that in some very specific cases, it's not difficult to describe or understand the gluing at all. And in those cases, you leverage that in your favor to sort of explain what the representation varieties look like and stuff and compute things. But what I was going to say was that for ciphered homology spheres, Pintushel and Stern have sort of more or less, they made the first stab towards computing all of these moduli spaces and whatnot. And there were further refinements due to others, but like they computed already. I think they gave an algorithm to compute the Instanton homology of any Briescon homology sphere.
Really, you're using the S1 symmetry and taking a symmetric metric, right?
No, you don't need to do that. It just so happens that you get lucky that all the indices are going to be even. So there are no trajectories. So you just need to look at the representation varieties, and those have a concrete description as moduli of some linkages or something like that. And you can appeal to GIT techniques from algebraic geometry to deal with it, or you can explicitly describe Morse functions on it
so
as well.
Boundaries are zero, so you're reduced to the sort of logical problem of understanding flat connections.
Yeah.
Flat connections. It's a variety that you have done.
Yeah. And I mean, this could potentially also have singularities or whatnot, but these guys basically are able to show that it does not matter. It does not affect your computation. So there is, I mean, they create their own version of perturbations that they use in their specific framework that gets the job done, which is neither a cylinder function, neither of Tobbs's or Uhlenbeck's or any of these perturbations. And that is good enough for their context. So, yeah. Anyway, I'll definitely continue this story in the next talk and only mention the results of Pintushel and Stern, and if anybody wants a more extended discussion, I'm happy to chat with them about it. Oh, I think somebody has raised their hand in the chat.
His hand has been up right through, but I don't know.
Oh, I see. Okay.
No, I actually had a
You have a
question. Can you hear me?
He has a
Yes.
question.
Can you hear
Okay.
me?
Yes.
Can you hear me?
Yes.
Okay. Yeah. So the question is, regarding this model thing, I mean, it seems like if you have asymptotically on the two ends the same connections A, then you can glue them up and get a 4-manifold. And then the index of the Dirac operator is the signature, which is divisible by 8. Is this sort of the reason why mod 8 comes up?
I'll ask that question.
Yeah.
So you said that in that mod 8 thing,
Mhm.
is it that if you have the same color cylinder, you can glue the
Yes.
ends together and you get a 4 manifold and the index of the signature is divisible by 8? Is that why you get the 8?
Yes, yes, you get S1 cross Y, and if you use the index formula, what the only thing that matters is 8 times the second Chern class of this connection, and since the second Chern class is always an integer, you get that it's 8 times an integer.
Thanks.
Yeah, that was.
Okay. All right, then I'll turn off the mic.
Yeah.
You get stopped for it.
Oh, I just exited, so that may have stopped.
Yeah, that's.
I guess we
Oh no, it's still recording over here, I think.
Yeah, I think everyone is still.
You need to
just
leave.
exit the meeting. Even that screen can.
Okay. Sir, shall I stop?
Yes, it stopped here as well.
So,